Patterns, pattern designs. Here we see three versions of the same form of pattern. In the first one we've got a small square, 3 by 3, with the blue diagonal and red tiles on the other diagonal, apart from the one in the very centre. Another version of the pattern, larger version, is the second one where we've got 5 tiles along the diagonal and the other diagonal has the red tiles apart from the one in the centre. And the third version, larger again, more tiles along the diagonal and red tiles along the other diagonal. So if we were to look at the patterns and count the number of tiles required for the pattern, we would see in the first version we need 3 blue tiles and 2 red or brown-red tiles. In the second version we need 5 blue tiles and 4 of the red tiles. And in the third one we need 7 blue and 6 red. We also need a lot of white tiles, and the number of white tiles varies considerably from the first one to the third one. So a question might arise in respect of patterns like these. So for the given pattern of tiles, and for the fifth element in the sequence, find the number of blue tiles, and also find the number of coloured tiles, red or blue. So we're saying that this is the first term, the second and the third. If we were to move 2 more, how many blue tiles and blue or red tiles would we need? So from observation, in respect to the first 3 patterns, taking the first one, in the first pattern we have 3 blue ones, 1, 2, 3. We have 2 reds, 1 and 2. We could count the whites while we're going, 1, 2, 3, 4, and the total 3 times 3 or 9. Observing the second one, we would find 5 blue tiles along the diagonal, 4 reds, 16 whites, and 25 in total. The 16 whites are 1, 2, 3, and 4, and there's 4 groups of them, 1 here, 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 and here. So 4 times 4 or 16. And the total number of tiles, 1, 2, 3, 4, 5, times 5, 5 rows and 5 columns. In the third set, third pattern, we have 7 blue, 6 red, 36 white now, 1, 2, 3, 4, 5, 6, 7, 8, 9, times 4 is 36, and a total of 49, or 7 by 7. So if we look now at what we were asked to find the number of blue tiles in the fifth element. So finding the number of blue tiles, in the first one we had 3, then 5, then 7. So we could probably guess that it's 3, 5, 7, 9 and 11 because it's an arithmetic sequence. We could also do it more formally and say that A, the first term in this sequence, is 3, and the common difference between 3 and 5 and 7 is 2. So using the formula for the nth term of an arithmetic sequence, we would say Tn is A plus n minus 1 times d. But we know values for A and d, so substituting them now for T5, the fifth term, we get A is 3 and n is 5 minus 1 times d is 2. So 5 minus 1 is 4, so 4 times 2 is 8, 3 plus 8 is 11, and that's the fifth term. So there are 11 blue tiles in the fifth term of this pattern. We don't have to draw it, we can work that out. Now, finding the number of coloured tiles, red or blue, in the fifth term. Once again we return to the pattern, and in the first one, if we counted the red and the blue, we'd have 3 blue and 2 red. So a total number of coloured tiles, 5 coloured tiles. In the case of the second pattern, we had 5 blue tiles and 4 red, or a total, in terms of red or blue, of 9 coloured tiles. And in the third one, we had 1, 2, 3, 4, 5, 6, 7 blue, 6 red, or a total of 13 coloured red or blue tiles. So here we have a total of 5, 9 and 13. So our sequence now for the number of coloured tiles, 5, 9 and 13, if we were asked to find how many in the fifth term, we would probably see that this is arithmetic. 5 plus 4 is 9, plus 4 is 13, plus 4 is 17, plus 4 is 21. So 21 in the fifth term. But if we were to do it formally, we would say, well, the first term, A, has 5, and the common difference between each of them is 4. 5 plus 4 is 9, 9 plus 4 is 13. So we can now use that in the general equation. The general equation for the nth term is a plus n minus 1d. But we know values for a and d. And we're also not interested in n, but specifically the fifth term. So t5 is equal to 5 for a, plus 5 for n in this case, minus 1 times d, which is 4. 5 minus 1 is 4. 4 times 4 is 16. 5 plus 16 turns out to be 21. So 21 red or blue coloured tiles in the fifth version of that pattern. We're now asked, if the total number of tiles in the fourth pattern is 81, find the number of tiles in the general term Tn. So we now know that the first three had 9 tiles, 25 and 49 tiles respectively, counting all the tiles, and we're told that the fourth pattern has 81. If we look at the differences here, we can see that the first difference is 16, the second difference is 24, and the third difference is 32. And that suggests that this sequence is not arithmetic. So another way of looking at that is that really we might consider these differences as the first set of differences. We know they're not arithmetic, but we'll count them as the first set of differences. If we take the difference between them again, the difference between our differences, our first set, we get the difference between 16 and 24 is 8, and 24 and 32 is 8. So on the second line, these differences are coming out the same. So for this reason, we can say that the sequence is quadratic. So while we don't get a common difference after one go, we get it after two. So this sequence is quadratic, and we can now use equations for that. The equation we use is that Tn is an squared plus bn plus c. That's the formula for a quadratic equation. But in addition to that, it's always the case that the a value is equal to half the second difference. So the a value here is half the common second difference of 8. So not only do we know that Tn is an squared plus bn plus c, but we know the value of a. So we can progress knowing that a is equal to 4. We also know that the first term is 9, the second term is 25, and the third term is 49, etc. So, solving for b and c, we can now say that the general form is an squared plus bn plus c, but in our case, a is 4. The first term, which we know has 9 tiles, is 4 times for the a, 1 for the n, so 1 squared, plus b, we don't know, times 1 for the n, plus c is 9. And for term 2, we know there are 25 tiles. It was a 5 by 5 square. So it's 4 for the a. N squared 2 is n. So it's 4 2 squared plus b times n is 2 plus c. So we have two equations now for t1 and t2. But really, because we have an equals here and an equals here, we really can forget about the t1s and the t2s, and we have equations now in b and c with numbers. So simplifying, we get 4 for 4 1 squared, plus b by 1 is just b, plus c, or 4 plus b plus c is 9. In the second term, we get 4 2 squared, that's 2 by 2 is 4, 4 by 4 is 16, 2b is 2b, and the c, so we get 16 plus 2b plus c is 25. So we now have two equations in b and c, And we can even simplify these further because we have a number on both sides. So taking the numbers to the other side, we get b plus c equals 9, taking the 4 across, minus 4 is 5. And 2b plus c is 25, taking the 16 that was there across is 9. So this reduces now to two equations. The first one, b plus c is 5, and 2b plus c is 9. And we just have to solve those two simultaneous equations for b and c. So if we write them out as two equations, b plus c is 5 and 2b plus c is 9, and we subtract one from the other, taking the 2b from the b, we get minus b, the c's cancel, and the minus 9 from 5 leaves minus 4. So minus b is minus 4, or b is 4. So we're now in a position that we know the value of a, which we had as 4, and the value of b, which is now 4. So from the first equation, b plus c is 5, we say b plus c is 5, but we know b, so 4 plus c is 5, so c must be 1, or 5 minus 4, which is 1. So we now have the three values a, b, and c. So the formula for a quadratic term here is an squared plus bn plus c, but we know that in this case a is 4, b is 4, and c is 1. So the general term for our set of tiles is 4n squared plus 4n plus 1, substituting a, b, c into these equations. If we wish to check that, we can put in the values for the first term, the second, and the third, or indeed any. But taking the first one, when n is 1, we get 1 squared for n is 1, plus 1 when n is 1, plus 1. Or 4 plus 1 is 9. 9 tiles in the first set. In the second set, when n is 2, it's 2 squared. 2 by 2 is 4. So, and then 4 times 2 for the 2n plus 1. 4 by 2 squared is 16. 4 by 2 is 8, plus 1. Again, 25 tiles in the second set. And in the third term, 4 by n is 3, so it's 3 squared, plus 4 by n, which is 4 by 3, plus 1. So 3 squared is 9, 4 by 9 is 36, 4 by 3 is 12, plus 1, a total of 49. So 9, 25, and 49. And the number in the fifth term then, we just use the formula, T5 is for 5 squared, because we're interested in the fifth term, plus 4 times 5 plus 1. 5 squared is 25, times 4 is 100. 4 by 5 is 20, plus 1, or we get 121. And that's our answer, the number of tiles in the fifth term. Now, this shouldn't surprise us because the original series was 9, 25, 49, and we were told it was 81, and we're now predicting 121 in the fifth one. But if we look at it, in the first one we had 3 squared because it was a 3 by 3 square, then a 5 square, 5 by 5 for 25, 7 squared for 49, 9 squared for 81, and not surprisingly 11 squared, 121 in the fifth set.